This video is going to talk about gravitational potential so we can relate it to an electric potential. Let's say I have two balls on a table and two balls on a bookshelf. If I look at the height of the table, it's going to have a certain potential. So I'm going to define that actually as a function called psi. That's the Greek letter capital psi, P, like PSI. And that's going to be our gravitational potential. So what I know is if I take the objects that are affected by gravity, objects with mass in other words, and multiply them by the gravitational potential psi, that'll give me the potential energy. So mass times psi gives me the amount of potential energy. So it makes it easy near the Earth's surface to see that gravitational potential is equal to GH. Now the bookshelf also has a gravitational potential. It's different than the table because it's higher than the table. So the bookshelf has its own, let's call it psi subscript b, and I can also calculate the potential energy of every object up there at that potential. So that would be the mass times the object times the potential. So mass times psi b. Every object up there has the same potential even though they have different potential energies. So in a way we've normalized the energy by looking at the potential. So in this case, psi for the table is greater than psi for the bookshelf. So if I take a ball, let's think about this question. If it rolls off the bookshelf, what happens to the kinetic and gravitational potential energies as the body moves from high potential to lower potential? So in this case, as it moves down towards a lower potential, the kinetic energy will increase. So the gravitational potential will decrease. So as I move to a lower potential, kinetic increases and potential energy decreases. How much work is done as a ball moves parallel to an equipotential line? So the ball rolls across the top of the bookshelf. How much work is done? Well, work is force times distance, and they have to be parallel to each other. But in this case, gravity goes down, and the ball is moving left to right, so they're not parallel to each other. So if you move along a potential line, no work is done. And finally, the direction of the G field. Well, the direction of the G field at any point on the potential is going to be perpendicular to the potential, and in this case, for gravity, it's going to be going down towards the source. You've probably seen images similar to this one online, and they'll put like a black hole or a planet or something in the bottom of that little well. And what you're looking at are actually gravitational potential lines. Here's some of the key takeaways. Energy can be determined using equipotentials. Work is done when motion is between equipotential lines. Work is not done when moving parallel to an equipotential line. Field vectors are perpendicular to the equipotential lines.